Hi everyone. We are going to start off again talking about quantum numbers. So remember that we said that there are actually 4 quantum numbers that we can use to describe orbitals or how electrons are distributed in terms of space, and that's going to be through their quantum numbers. So again, we changed this to where it's going to be 4 now instead of 3. So the first one that we got to in class was about principal quantum number, and we said we're going to symbolize that with N. Ultimately, principal quantum number is just energy level. That's it. So we know that it's going to start off at 1, so at N equals 1, we have already said that that's going to be ground state. So that's where the electron is going to want to be because it's going to be closest to the nucleus. So as N increases, that means that ultimately my orbitals are going to become larger, the electron's going to spend more time away from the nucleus, and an increase in N also means that an electron's going to have a higher amount of energy because it's going to be less attracted to that nucleus since there's so much distance separating then the electron from the nucleus. So because it doesn't have as much Coulombic attraction, it's going to have a higher amount of energy, okay? So for example, I would definitely be most stable if, like, Ryan Reynolds were to come into the room right now if I were really close to him, like if I were hugging him. So it would take a lot of energy for somebody to hold me back and separate and have there be distance between the two of us. So my Coulombic attraction has to be, the Coulombic attraction that we will feel will be weaker because there's a lot of distance that's separating us, and I will have a high amount of energy because I will want to be very close to him. Just an analogy. The second quantum number is going to be the angular momentum quantum number. We're going to symbolize that with an L. This quantum number, like we said, is going to define the shape. It's going to define the shape of the orbital. So what kind of shape or what kind of an electron density are we going to see as electrons move around in specific areas? So when we think about quantum numbers, we'll do some practice with this tomorrow because we know that N, energy level or principal quantum number, could be as low as 1, and then from what we know can be as high as like 8 or 9. When we find our value for L, we're going to do that by taking N minus 1. So it said that allowed values of L are integers ranging from 0 to N minus 1. So what does that mean? This means if the value of L is 0, the orbital type that we're going to be talking about is S. If the value of L is 1, the orbital that we're going to be talking about is P. If the value of L or angular momentum quantum number is 2, I'm going to be talking about the d orbital, and if it's 3, I'm going to be talking about the f orbital. The ones that we should be focusing on are s, p, and d. We probably will not focus on f so much, just because there's a lot of debate right now about what the f orbitals actually look like. Okay, so also talking about shape. Let's add to this that for the shape of S, the S orbital will look spherical in shape. Okay, so S is spherical. The P orbital is going to be dumbbell in shape. So S is spherical, P is dumbbell, and then the D, for the most part, will look in the shape of a clover leaf. So I have spherical, I have dumbbell shape, I have clover leaf, and then F, again, we're going to kind of just forget that it exists, even though it technically exists. We just don't really know what overall shape that will give us. Okay, third quantum number is called the magnetic quantum number, and we're going to denote magnetic quantum number with the symbol M sub L. M sub L. So this is just describing orientation. So the principal quantum number tells me what energy level we're at. Angular momentum quantum number tells me the shape of the orbital. So am I in the s orbital? Am I in the p orbital? Am I in the d orbital? Magnetic quantum number tells me, are the electrons in the are lying along the x-axis? Are they lying along the y-axis? Are they lying along the z-axis? So it says the magnetic quantum number describes orientation, and that should be in 3D. We have allowed values, and they range from a negative L, which is my angular quantum number, to a positive L, which is my, again, my angular magnetic number there. So I could range from, for the s orbital, for one s, and then I could have 3 p orbitals, I could have 5 d orbitals, I could have 7 f orbitals, and we could go on because there's technically g orbitals, even though those are also in debate right now. But how did I get these numbers? Let's go back to L. We said for L, s orbital is 0. So if magnetic quantum number is dependent on L, that means that I can go from negative integers to positive integers of my value of L. So if I'm in the s group, I'm only going to have 0, right? So I only have one s orbital. And if you think about it, we're thinking about a spherical shape. I can really only orient a sphere one way in 3D. So it should make logical sense that I only have one s orbital. Let's talk about p orbitals. So for the p orbital, I can have 3. P here, the value of the type of orbital here for p, the value of the p orbital for L is 1. So when L equals 1, I'm talking about a p orbital. If I want to know my magnetic quantum number, I'm going to go from positive 1 to 0 to negative 1, okay? So that gives me 3 different orientations that the p orbital could have. Guess what? The dumbbells can be oriented along the x-axis, along the y-axis, or along the z-axis. Those are my 3 orientations for the p orbitals. So logically, this makes sense to us as well. So then d orbitals, because we're going from the value of L for the d orbital to be 2, I could go from positive 2, positive 1, 0, negative 1, negative 2. That gives me 5 values. So D can take 5 different types of orientations in terms of what shape its electron cloud can make. And then theoretically F should give me 7 different shapes, okay? So this is table 6.2 in your book. It's just going through and telling you if this is my value of N here, so these are the energy levels that I'm at, these are the possible values of L I can have, and then this is how I would start to write with my electron configuration. Okay, we're going to do practice of this. I don't care right now that we know this, because this is what we're going to focus on tomorrow in class. Right now, all I want us to do is understand what each of the quantum numbers mean, and then what their symbols are. So again, orbitals with the same, let's do 2 new vocab words. Orbitals with the same value of N are forming what we would call a shell. But if we have different orbital types within a shell, so that means if I have an s orbital and a p orbital, those are called subshells. So the shapes that I can make in an energy level are called subshells, and then the actual energy value is what we're just going to call a shell. So in terms of energies of these orbitals, so it's really easy to focus on hydrogen, which is why a lot of scientists will start off with hydrogen, just because it's very simple. So for a 1 electron hydrogen atom, orbitals are all on the same energy level. They all have the same energy. So if we have things that have the same energy, in science we call them degenerate, meaning that they're all at the same energy level, okay? But meaning that the ones that are on an energy level are going to be the same. So what that means is 3s, 3p, 3d are degenerate all within one another because they're all on that same energy level. 2s and 2p are degenerate because they're on that same energy level. They're on the same shell, what we